Y'all hear some news that'll put some fat stacks in everyone's pocket. Every American is able to pocket.
So now, when it comes to voltages, we have a bistable 555 timer right there. The output is high. We have a high input to the reset pin. Any amount of low input to the reset pin sets the output low, and it's going to stay that way. You can hold it down, doesn't matter how long it is. We need to give a low input to the trigger pin to set it back. We'll look at that coming up. But there you can see we have a pull-up resistor right there, keeping 5 volts at pin 4 because we're using 5 volts, the reset pin, until we close the switch. Then we get a direct connection to ground right there. And that is going to lead to the output going low. So what that means is the output connects to ground as best as it can. I used a blue LED to indicate when the output is connected to ground because we got positive supply right there. Red LED lights up when it outputs as close to the positive supply as it can, a high output. So now we come back to the bistable mode, 555 timer, output's low, and it's going to stay low because we press the reset pin until we give a low input to the trigger pin right there. So it's 5 volts, pull-up resistor is doing that, and that's where we're taking our measurement at pin 2, but it comes up to that switch there which connects to ground when you press it. So it doesn't matter how long we press it, any brief period amount of time, it's going to set the output high, and it's going to stay high until we reset it. And so that's setting it when you get high right there. So we'll zoom in, and there you can see trigger pin right there. Main thing to remember is reset pin is more powerful if you're holding both of them. But yeah, we got 5 volts thanks to the pull-up resistor until we close the switch. Then we get a connection to ground. And when the output's high, that means you got as close to 5 volts as you can in this case. Because we're using 5 volts, it does fall a little bit short, but I use a red LED to light up in that case. When the output's low, I usually use a blue LED to indicate a low output. So now we come back to the bistable mode 555 timer right there. Output's going to stay in whatever state it is until we change it. This is the output voltage we're looking at, third pin down right there. And so it goes all the way down to 0 volts when the output's low, does a really good job, but falls short of the 5 volts when the output is high. It'll do a little bit better without the LED there, the load drawing current, but still we fall short.
Sam, since this is your first Get Holiday Ready sales event, let me introduce you to the full lineup of Ford SUVs. Keep it festive, Morgan.
This was the very first transistor, and it was made in 1947. By 1978, the industry had advanced to integrated circuits with features just 1 micrometer large. That's 50 times smaller than a human hair, and was done on a machine that cost about $2 million. I want to replicate that capability in my own shop, so I'm going to build a photolithography machine with the goal of hitting 1 micron features. But, you know, it's 2024, which means I can cheat and use modern technology to speed run through the last 30 years of progress. And hopefully make it a little cheaper than $2 million. If you're new to the channel, here's a quick overview of what's going on. There are hundreds of steps to make an integrated circuit, but arguably the most important step is called photolithography. It's the process of transferring a pattern into a photosensitive resin that's on the wafer. That pattern is then used for every other step in the process of making a chip. It's basically the same idea as cameras and film emulsion, the light-sensitive resin that's used in SLA printers, or the resist that's used to manufacture PCBs. The only difference really is in size. Chips are very small, and so the pattern we put on the chip also has to be really small. I've dabbled with photolithography a little bit in the past, and the machine I made was, well, charitably, it wasn't very good. In fact, it was basically unusable other than as a demonstration. I've also done some electron beam lithography in the past, and it's perfect for really small features. I've been working on some vacuum transistors that have gaps just a few hundred nanometers wide. But my machine isn't really designed for patterning large areas. So if you watch my DIY camera sensor video, you'll have seen all the issues I had with stitching multiple fields together to form like a bigger chip. So I have two goals with this project. First, I really want to hit that 1 micron feature size. It's, just like a nice round number, and it coincides with a historical kind of pivotal moment in the industry. In 1978, GCA introduced the MAN 4800 DSW. This was the first commercially successful wafer stepper that used reduction optics to print patterns, and it was basically a huge jump forward for the industry at the time. So I figured the 1 micron mark would be a good milestone to aim for. Also, and this is just kind of fun, the machine retailed for $450,000, which in today's money is about $2 million bucks, making the equivalent of a $2 million machine in my own shop. I don't know, it kind of just sounded like a fun challenge. The second goal was to write patterns over a large area. With a good microscope objective, it's actually not that hard to hit sub-micron features, but it's very challenging to do that over a wide area consistently. With those goals in mind, let's start designing this machine. The device I made a few years ago was constructed from aluminum extrusions, 3D printed components, and basically bubble gum. I kind of just assembled it as I went, and it really wasn't great. I want this new machine to actually work reliably, so it's time to fire up the old CAD program and pretend to be an engineer. I designed a frame that let us mount the motion stage at the bottom and all the necessary optical stuff at the top. It also doubles as an enclosure. Photoresist is sensitive to ultraviolet light, so there are large yellow acrylic panels to filter out anything that could expose the resist. I decided to go with a sheet metal design for this project. I've never really done sheet metal work before, but it made sense for this machine. 80/20 extrusion is a pain to work with in my opinion, and I wanted something more professional than Home Depot wood panels. Unfortunately, I don't really have any sheet metal capabilities in my shop. I have CNCs, but they aren't really designed for large sheet fabrication. Luckily, you can order laser cut parts from Send Cut Send. The process is really easy. Just design in CAD, export a DXF or step file, and upload to their online system. They also have bending services, which I used liberally on these parts to make assembly a little easier. I'm a Fusion 360 user, and Fusion has a pretty decent module for modeling bent parts. You punch in the bending parameters that Send Cut Send provides for their different materials, and then you just start creating bends and flanges. I fired the parts off to Send Cut Send and got to work on the optical system. This is basically a DLP projector in a dev kit form from Texas Instruments. There are a few main components to this. There's a lens section here, which we'll be removing because we don't need a projection lens. There's the DMD chip inside of the device, and we'll see that in a minute. And then there's a bunch of complicated optical components down here to couple 3 high-power LEDs into the projection system. So one of these LEDs, the blue one, we'll be replacing with a UV LED. And we'll keep red and green as they are because we can use those for inspection and alignment purposes. So the next step to do is pull off the projection lens and add in our own adapters so we can start adding optics that we want in front of this system. And now I'm going to roughly get all the optical components in place just to make sure everything fits and see if I need to make any more cage plates or if some of these don't work or whatever. So we've got a lens, a beam splitter, another lens, microscope objective, and this is a camera. Okay, I'm going to take a pause for a minute to explain the optical system, kind of like all the different things going on here. So the heart of the system is a digital mirror device, or a DMD. These are made by Texas Instruments, and you'll see them on DLP projectors. It's basically like a matrix of little micro mirrors that can be individually addressed, flipping them back and forth, turning it essentially on and off. So when they're flipped one way, they send light to the projector lens, and when they're flipped the other direction, it just sends light off into nowhere, and you get a dark pixel. But the trick here is we can take the projection optics, remove it, and put some kind of reduction optics, like a microscope objective. And that will project a pattern down to a small size on your substrate. And this is basically what's called a maskless lithography machine, because we don't have any mask. We're just making the pattern digitally on a computer and displaying it with the DMD. This is a very well-established route to take. There are hundreds of academic papers that use this. Real commercial lithography machines will actually use a DMD internally, and there's even a bunch of YouTube channels like Sam and Huygens Optics that have done this as well. So this is nothing new. I'm just doing it again, kind of with my own take on it. My original plan was to build a direct write laser machine, very similar to the first one I built a couple years ago. But I changed my mind when I ran across the Hacker Fab group. This is a group of like self-organized students at CMU that are building an open source lithography fab. So it's all the things you need to build a chip, you know, spin coders and litho machines and process development. It's all being documented and put online. So I decided to go their route and pick up a DMD similar to what they are using. My system ended up being quite a bit different than what they have, but it was really helpful having all this stuff pre-documented. So if you're interested in open source litho, definitely go check it out. They're doing some really cool stuff over there, and it's all accessible online. The actual optics are pretty simple. UV light is projected onto the DMD, which is toggling those mirrors on and off to form an image. This generates a diverging beam that comes out, and we collimate it with a lens. It then hits a beam splitter. Most of that light continues straight down into a microscope objective, which focuses it down onto the substrate. Some of that light is absorbed by the photoresist, and some of it bounces off and goes back the way it came, hits the beam splitter again, and is redirected into this horizontal arm. Another lens takes that beam and focuses it onto a small USB camera, which we can use for alignment and focusing. And that's basically it. It's pretty simple as far as optics are concerned. We also have to replace the blue LED with ultraviolet LEDs. I've never used solder paste before, so please forgive the crimes I'm about to commit. They soldered up a bit wonky because I don't know what I'm doing, but they work fine, so whatever. Then we need to drill some holes in the base plate so that the DMD can be mounted to the rest of the frame and assemble the whole optical engine.
Are you looking for more in this world? Are you ready to be part of something?
A week or so later, the Sen-Cut Sen parts have arrived, and it's time to start assembling the frame itself. The frame is made from 1/4-inch thick mild steel, while the two DORP side panels are made from a slightly thinner cold-rolled steel. And then there's like a back panel, which is just a really thin aluminum. 1/4-inch might have been a little overkill, but I want it to be super sturdy because any vibrations or movement of the frame will directly impact the resolution. So I kind of messed up the design of this, but I think it'll be recoverable. Basically, there's a bow to this bottom plate. That's just the nature of this type of metal. So this is just A36 mild steel. It's not the fault of the laser cutting service. That would happen if you bought this sort of plate straight from the metal distributor. So what I should have done is put a vertical section here bent upwards, and then the same on the front to turn it basically into a box. If we look at this piece, this is basically what I should have done. I needed a bend on the left and a bend on the front, and that makes this surface remarkably flat for being, you know, a piece of just bent sheet metal. Luckily, having it fully assembled seems to constrain the structure a fair amount, and it's relatively flat. To get these parts ready for painting, I first had to deburr all the laser cut edges. Laser parts are way cleaner than plasma cut, but there's still a sharp burr that needs to be removed. Sen-Cut Sen offers deburring services for a very reasonable rate.
Hey guys, welcome to Electronics. In this video, we are covering the characterization of a crystal resonator, like this one here. We are going to characterize the crystal using measurements from a state-of-the-art VNA. With the measurements, we are going to go to the whiteboard to see how we model the crystal as an electrical circuit. And using the measurements, we can calculate the values of each component on the electrical model. Measuring crystals like this is not trivial because we need to properly configure the measurement device, because a resonator like this has an enormous skew factor, and this can lead to wrong results if the measurement is not configured configured properly. Having the electrical model of the resonator allows the designer or the engineer to create circuits that use the crystal, like oscillators or filters. And even more important than that, as you are going to understand how the crystal behaves electrically, look into the crystal as a combination of series and parallel LC tank resonances, you will be able to change the response of the crystal, like changing the center frequency of an oscillator. This is real engineering, because you're watching All Electronics. For this experimentation, I just got one crystal resonator and soldered it here on this PCB using two SMA connectors. The measurements that we are going to perform to get the series and parallel resonances of the crystal require just an S21 trace, and that is the transmission parameter between one port to the other. So any kind of spectrum analyzer with tracking generator will also work for this measurement here. You don't need a fancy VNA to measure a crystal. The crystal is connected to the VNA using the two ports because we are going to measure the transmission between one port to the other. And we see that this crystal is marked as 3.68 MHz. So this is the first clue that we have for configuring the equipment. Center frequency 0.60 MHz, and you're going to use a very narrow span like 100 kHz. You see this trace is a reflection measurement. We are going to change that for a transmission measurement S21. And now we start to see some response here. But this is looking very strange. And this is because this crystal here, our crystal resonator, has a very high Q factor. Actually, this curve here is a false measurement of the very sharp peak and sharp valley that this crystal response has. To properly configure the equipment, let's first go to the amplitude and place the reference position there on the top. Let's go to the sweep configuration and increase the number of.
Cover your place in rugs. Done.
Increase the number of points. You see the difference it makes? Look at this. If the peak is very narrow, you need to have enough points to capture the peak or the valley. If you don't have enough resolution, we would miss the peak and the valley. What's happening now also is that the resolution bandwidth is too large. So we can reduce the resolution bandwidth, let's say to 1 kHz. Look at that. And actually, when we perform the last measurement, we are going to use an even lower bandwidth, like 100 Hz. You see that now the sweep is much slower and the peak changed a little. You saw that. You just saw something very important. How the setup of the equipment can change the measurement, leading to false results. And for devices like a crystal resonator that have very narrow peaks of resonance due to the large Q, if you misconfigure the equipment, you even will not notice that the device is inserted on the equipment. And this can lead to a lot of confusion. Suppose that we had just turned on the equipment and the frequency span was much larger. Look at this, guys. The response almost disappeared. Well, let's go back to the measurement. Here we have the base response of a crystal resonator. We have a series resonance and a parallel resonance. Why this is a series resonance? Because you can see that the transmittance increased. So at this resonance peak here, let's get its frequency. At 3.685 MHz, the crystal is looking like a short. But just at a slightly higher frequency, the crystal looks like an open circuit. Look at this. The S21 here goes to -80. We call this frequency the series resonance frequency, and this frequency here the parallel resonance frequency. We can get a second cursor here to go there. Marker 1 series resonance, marker 2 parallel resonance. Let's optimize the measurement a little more. We can get a marker, guys, and put more or less here on the center of both responses and set this frequency to be the center frequency. Now we reduce even more the span. Now we have the measurement very clear on the screen, series resonance and parallel resonance. I imagine you are asking yourself why we have different resonance points and what these resonances mean. We are going to go to the whiteboard to take a look on that. What's interesting to see is that we have two resonant behaviors. A series resonance where the energy passes through the crystal because it looks like a short, and a parallel resonance where the crystal looks like an open circuit. These two modes of resonance occur at different frequencies, very near but different, but the crystal is marked to just one frequency. The manufacturer marked the crystal for one frequency. And what's happening here is that every crystal is specified for one of the resonant modes for a very specific condition. For example, a crystal can be specified for parallel resonance, and also a specification of what parasitics the crystal will see on its terminals is required. For example, we can have a crystal for 5 MHz for parallel resonance with a load of 10 picofarads. That means that the manufacturer will cut the crystal and tune the crystal so it presents its parallel resonance exactly at 5 MHz when presented with 10 picofarads of capacitance in its terminal. Different circuits can benefit from the different resonant regimes. You can have oscillators that use the series regime or oscillators that use the parallel regime. This video is based on an article I wrote where I explain this in more detail. The link is in the description of the video. Take a look on the article. The difference between using a VNA and a spectrum analyzer with tracking generator is that the VNA makes a vector measurement. The receivers of the VNA can detect the phase of the signal that is passing through.
This helps me pay for my bills. Sign up directly on the app. Choose your own hours. Get paid to deliver.
Here's an interesting problem. How do you create a delayed duplicate of a sound without recording it to some sort of storage medium?
Back in the days before computerized audio processing and cheap abundant memory, this was a prime engineering issue. That's because at that time, the only practical electronic implementation of an audio delay effect was large, bulky tape echo machines.
These machines worked by recording an input signal to electromagnetic tape and then playing it back with a time delta. Of course, you could always decide to go no tech and use a wide open space with a reflective surface in the distance to create an echo.
This works because it takes time for sound to travel through a medium such as air.
In the late 60s, two electrical engineers named Sangster and Tier managed to implement an idea that was essentially a unique hybrid of the two concepts I just mentioned, the bucket brigade delay. This circuit first splits an audio signal into analog samples, which are then routed sequentially through a chain of transistors and capacitors, similar to how sound travels through a medium. At the output, the signal is reconstructed from those samples. And because passing the samples along the transistor capacitor chain takes time, the reconstructed signal will be delayed compared to the input, with the length of the chain determining the total delay time.
In this video, I want to reverse engineer the architecture of a classic bucket brigade delay, recreate a bare bones version on the breadboard, and then use a proper BBD chip to implement a simple audio delay effect.
We'll start by investigating the first stage of a BBD, the analog sampling subcircuit, which splits the input into transmissible chunks. Okay, but what does that mean exactly? Well, in electronic circuits, an audio signal is represented as a swinging voltage, like this triangle wave. To extract a sample from this means that we probe the signal at any point and store whatever value we read. If we do this continuously and in regular intervals, we get a series of samples that resembles the input. But unlike a swinging voltage, those samples are discrete and can be easily held in a capacitor, allowing us to control when and how they move. They move through.
well alone.
Here's an This is why Sangster and Tier call this technique a charge deficit transfer. The deficit has moved from cap 1, which is now full, to cap 2, which is now missing 1 volt. And because we give cap 2 a strong push from below via the preceding JFET's gate voltage, this will work even if cap 1 starts out completely empty. Of course, this doesn't just work for a single transfer. We can add an arbitrary amount of JFETs and capacitors all set up in the same way to increase the number of transfers. Charge will flow from right to left in just the same way, while the deficit travels from left to right until it reaches the end of the chain. Note that to automate this circuit's operation, we'll need a second clock signal that is the exact inverse of our existing clock to drive every other JFET. Also note that each cap is only carrying information on every other clock pulse. It is either full, which means it's not carrying information, or at a charge deficit, which means that it is carrying information. Next, we'll want to combine the charge deficit transfer idea with our previously established sampling.
Hi, we all know what a switch is. We might not know how to wire it, but what I'm trying to say is MOSFET is basically a switch. You use it as a switch. It connects and disconnects. You can use it as an amplifier, but who uses it as an amplifier? MOSFET is a type of transistor that has revolutionized our technology. Well, right after BJ transistors revolutionized and pretty much replaced all those pesky vacuum tubes, they can be made to switch on and off at gigahertz speeds, or made to switch thousands of amps on and off, or handle thousands of volts. You may remember from my old video how single dumb switches can be put together to create artificial intelligence stronger than what a human brain can operate at. In some cases so far. Middle Eastern, but I said no beard. No beard, I said. No beard. It can't imagine a Middle Eastern man with no beard. Those computers run on single dumb switches that are MOSFETs. Of course, computers with artificial intelligence have to be trained to be able to do anything useful. You can learn all about AI at my sponsor brilliant.org for free for 30 days from my link below. More at the end. Let's learn about MOSFET transistors though. It is typically a three-legged component as usual. The legs are called gate, drain and source because I don't care why they named them like that, and it acts like a switch between drain and source terminals that can close and open by a voltage on gate. So for example, let's learn a bit more before using this stuff. I think we have to start at fetus stage. I explained in my diodes video that there are two general types of semiconductors, P and N, which can individually conduct electricity pretty well. They are both electrically neutral, but when you fuse them together, P shows positive behavior as if it lacks electrons, or rather has holes. And N shows negative behavior as if it has extra loose electrons. So some electrons move from N to P. So they will be extra happy if you place a voltage across them to move electrons in their desired direction. But if you place the voltage backwards, you can't push electrons backwards and the current is blocked. So you have a diode. Now imagine we have a big P-type silicon and we make two regions of N-type silicon on the sides and connect two terminals to it. It would be as if we have two reverse diodes back to back, so current can't flow either way. Let's connect another terminal to the main P-type silicon we call a substrate. Then we grow a piece of thin glass up there, oxidizing the silicon between the two N terminals for insulation, and deposit a layer of aluminum on top of it. The aluminum terminal is called gate. Now, if instead of NPN we had all Ns, there was no blockage, we had a conductive semiconductor that current could flow through in either direction. If only there was a way to drive the P out of the P semiconductor and turn it into N. But there is! That is a capacitor with two conductors and a glass dielectric in the middle. We put positive voltage on the gate and a negative on substrate and suck the electrons off the aluminum plates, which in return pulls electrons in the P region. And we know P is happy to have electrons. But to what extent? P is like, oh yeah, fill all my holes with electrons. Give me. No, okay, stop it, I'm done. Let's stop, please, no more electrons. So we fill the receptive holes in the P semiconductor, which takes a minimum voltage we call threshold voltage, or VTH. Any voltage above that sucks extra electrons into a thin channel close to the dielectric that forces the P out of that channel. And now the channel is a semiconductor with excess loose electrons and starts behaving like an N semiconductor. There is no blockage anymore. Our transistor turns on and the current can flow in either direction through a thin channel we created by converting P semiconductor into N by force. So we call this an N-channel transistor. Now, to have a separate voltage for gate substrate and another between the two terminals makes it a bit complicated. So for most such transistors, they just tie the substrate to one of the terminals. They call this new leg source and the other leg drain, like I mentioned before. And so we have what we call a FET, or field effect transistor, because it works with the electric fields in the gate to substrate / source capacitor. The MOS added to the FET stands for metal oxide semiconductor, which refers to the popular material they're made of. There are different types of FETs out there, all work with the same principles, and MOSFET is the most popular between them. Of course, we can flip the NPN configuration into PNP, and now we have to convert N into.
Hey Meta, remind me who's on my guest list.
Here's who's on your guest list, Tina Shea.
It's about to go up.
Hey Meta.
Recently, I've been thinking about what I could salvage from this old computer of mine. I saw a couple videos of people lighting matches with a laser diode from an old DVD burner, and since this is exciting, dangerous, and have the potential to blind you for a lifetime, it is perfect for YouTube. So in this episode of Hacked, I will show you how I extracted a laser diode and how I built a constant current source to use them properly. And at the end, we will see whether I'm capable of igniting a match with it. Let's get started. First of all, let's have a look at the DVD drive. As you can see, it is labeled with a class 1 laser warning. It is a low number because the laser is kept safe inside the case. Thus, this class is not capable of harming you at all. But right next to it, it says class 3B, which can blind you in an instant if the laser beam hits your eye directly. You have been warned. I started to open the case by removing the 4 visible screws. Then I took off the front plate and continued my tactic, which says see a screw, remove a screw. During this process, I also saved 3 more motors which could be useful for a future project. I continued to take the whole drive apart until I finally ripped out the heart, which is basically the driver head which moves over the DVDs. Here we can already see where the 2 diodes hide. Again, I used a screwdriver, soldering iron and some muscle force through my plier to take the whole construction apart. And I also found 2 neodymium magnets along the way. Those are always useful. Then I desoldered the flexible PCB from the diodes, used pliers to crush the glue and carefully removed the 2 diodes. Now I hooked up my positive wire to the top pin and my
Hey
Hey guys, Will here. Welcome back to the channel. Now today's video I'm going to be showing you the basic settings that I use to overclock an 8700K or 8086K processor. So if you've been watching my previous videos, you would know by now that effectively they're the same chip as each other. The 8086K just in most cases overclocks slightly better than the 8700K with slightly lower V-core voltages. So we're going to be using the Maximus X motherboard in this video, so the Asus Maximus X. I'm using the code, but the settings are basically the same for all of the Maximus X motherboards, and a lot of these principles can be applied to most motherboards. I am working on another video series that's going to go through all the various different settings, what they actually mean in order to fine-tune your overclock and actually teach you guys how to overclock as a principle and what all the different settings mean, that kind of thing. The purpose of this video is more just to give you a top-level overview of the settings that I used out of the box to achieve the results that I've been able to achieve, because I do get asked that a lot. Now, I kind of was reluctant to do this video because I think it's important to understand the principles, but in saying that, I do get a lot of questions from people just wanting to know.
That'll spook him a bit, give us an opportunity maybe. Oh, he's spun!
P2's gone off in Atwood Curve.
Hello guys, welcome to another iRacing race today in the F3 in the Mazda Challenge.
This carne asada looks amazing here. Check this out. How hard is it to make carne asada? Is it like an easy thing to do or what? Let me show you how to do it. We're gonna do this from scratch. So tell me what to look for in meat whenever you're cooking carne asada.
What we personally like is we like the boneless.
Stock up on everything merry and bright with 50% off Christmas decor and more at Hobby Lobby. Find trees.
This video was sponsored by Brilliant. Computers operate on a very simple principle. They run instructions one by one. Running each instruction requires several steps. Fetch the instruction, decode it, and execute it. But the question that often puzzles people is, how does the computer know to first fetch, then decode, then execute, and repeat this process in that order over and over again? The simplest answer to this question is the clock. A little device that produces an oscillating signal, which, working in concert with a few logic gates, orchestrates the computer's step-by-step progression through each instruction. Hi friends, my name is George, and this is Core Dumped. This video is not about how to implement clocks, but rather why the oscillating signal they generate is so important to computers. There's a great video from Ben Eder on how to implement a clock like this one. A clock signal can be thought of as a series of pulses, so it makes sense to think that each pulse prompts the processor to move one step forward. Our goal today is to learn how. As always, there are multiple ways to approach this, and I'm not going to present the best one, but the simplest and most intuitive one I could think of. Let's start by analyzing the clock signal. First, it's important to note that clocks can generate many different types of waveforms, but we focus on square waves because they take only two values, perfectly matching the binary nature of computers. Now, one aspect of the clock signal that is particularly important is the edges, the tiny portions where the signal switches from one value to another. When the clock signal changes from 0 to 1, we call it a rising edge, and when it changes from 1 to 0, it's a falling edge.
The wait is over. The Digi Anywhere USB Plus is back in stock and ready to ship. With its high-speed USB over IP technology,
to 0, it's a falling edge. The reason we aren't interested in the parts of the signal where the values remain constant is that nothing happens during those intervals. They're like dead zones where no events occur, and there's nothing for the system to react to. But edges are different. For example, we can build circuits that can be used to detect them. At first glance, you might think this circuit always outputs 0. An AND gate only outputs 1 if both inputs are 1. But since both inputs come from the same source and one is negated, it seems impossible for both inputs to be 1 simultaneously. But let's take a closer look, analyzing the input and the output over time. The input will be the clock signal. When its value is 0, nothing happens in the circuit. It's stable and nothing changes. When the clock flips to 1, the signal propagates to the left, but the inverted signal takes a bit longer to update. For a very brief moment, measured in nanoseconds, the AND gate receives a 1 at both inputs, causing it to output a 1. A fraction of a second later, the updated output of the inverter reaches the AND gate, turning its output back to 0. When the clock flips back to 0, the delay from the inverter occurs again, but this time it doesn't affect the output. And nothing significant happens until the clock flips to 1 again. The delay from the inverter once again causes the AND gate to output 1 for a brief moment before the inverter corrects the output, dropping it back to 0. If we observe the output of this circuit over time and compare it to the clock signal, we see something clear. A quick pulse is generated at every rising edge of the clock signal. In other words, we've created an edge detector, a rising edge detector. There are other types of edge detectors, but we are not going to go down that path. Instead, let's talk about flip-flops. But first, a quick message from Brilliant. There's one fact we all know about traditional studying. Reading books might not always be the most effective method. But fortunately, Brilliant is here to help. With Brilliant, you have access to dozens of different courses designed by professionals and specifically crafted, so you can interact with examples and improve your problem-solving. Part is you don't have to spend. You can access all sorts. Try everything Brilliant has to offer for free for a full 30 days and get 20% off in your annual subscription by accessing brilliant.org/coredumped or by using the link in the description below. And now back to the video. In my previous video on memory, we we discussed that a latch is a circuit capable of storing a 1 or a 0. The one I'm showing here is made of 2 NOR gates and is called an SR latch, which stands for Set Reset Latch. The output Q with the little line in the top outputs the inverse of the value stored, while Q outputs the value stored. Activating the S input causes Q to output 1, and this value is held even if we set the input back to 0. The R input resets the value of Q back to 0. When both inputs are 0, we're neither setting nor resetting anything, so the circuit simply remembers the last value. Notice that setting both inputs to 1 doesn't make sense because we shouldn't be trying to set and reset the output at the same time. If we do attempt it, while both inputs are activated, both Q and its inverted are forced to 0, which doesn't make sense. They should never output the same value. And not only that, but another issue arises when we set both inputs back to 0. In this situation, the circuit might end up holding either a 1 or a 0, depending on which input changes a few nanoseconds before the other. This creates uncertainty. A variation of this latch exists, which is quite similar but includes an additional input called enable. When the enable input is 0, the other inputs have no effect. We can only set or reset the latch by activating the enable signal. This variation is known as a gated SR latch. At this point, you might be wondering how all of this relates to the clock. Well, if we use the clock as the input for the enable signal, we get a behavior where the levels of the signal, 1 or 0, determine whether the latch can be modified or not. But there's nothing new here. That's the expected behavior of a gated latch. However, if instead of using the clock signal directly, we place an edge detector between the clock and the latch, things get more interesting, because now the signal level doesn't matter. For example, at this moment, the clock signal may be 1, but the edge detector is outputting 0. What triggers the latch's write operation is the rising edge of the clock, the brief moment when the edge detector outputs 1. And that's the key difference between a flip-flop and a latch. While both can be used to store a bit of information, a latch is level triggered, while a flip-flop is edge triggered. While this particular flip-flop triggers on rising edges, there are other types that trigger on falling edges. But this flip-flop inherited a problem, the invalid state, when we try to set and reset at the same time. Let's try to get rid of that problem. To avoid overcomplicating, I'm going to start by abstracting the inner SR latch. We can add a third input to the AND gates and make sure they never receive the same value, so only either the reset or set input is allowed through, but never both at once. If you think about it, the values of Q and its inverse are perfect for this, since they are always opposites. In this arrangement, the inputs are given new names, J and K. On a rising edge, J performs the set function, while K performs the reset function. But what happens if both J and K are activated at the same time during a rising edge? Well, it depends on the value currently stored. If the value is 1, only the K input will take effect, resetting the latch. If the value is 0, K will have no effect, but J will, setting the latch. In other words, if both J and K are activated during a rising edge, the flip-flop toggles its current value. A JK flip-flop operates as follows. When only J is activated, a rising edge causes it to set. When only K is activated, a rising edge causes it to reset. And when both J and K are activated, a rising edge causes it to toggle its value. This toggle feature is useful in various scenarios, but we are particularly interested in the following application. By permanently setting J and K to 1, by connecting them to the voltage that represents 1, typically 5 volts, the clock's natural oscillation causes the value to toggle automatically. This creates a new signal at output Q that periodically alternates between two states, effectively generating a new clock signal. Looking closer, we can see that since toggling occurs only on the rising edges of the original clock, the resulting signal oscillates at half the frequency of the original clock signal. And with this, we can
Floor Coverings International comes to you with a mobile flooring showroom and with one local team.
Let's talk about complex numbers. Why do electrical engineers use complex numbers? Complex numbers show up in Euler's relation. They also show up in the Fourier transform. And they also show up in AC circuit analysis with impedance. Let's start by understanding what the imaginary unit is. In essence, I is equal to the square root of -1. In EE, the convention is the letter J. A complex number can be represented by the expression below. The complex number z is set equal to the expression on the right, and consists of two parts. A is the real part of our complex number, and JB represents the imaginary component of our complex number. I want you to think of a complex number as a two-dimensional number. Looking at a familiar Cartesian plane, we can express a normal vector graphically by saying it is going 3 units in the i-hat direction and 2 units in the j-hat direction. Similarly, a complex number in this example can be interpreted as a vector from 0 to the point 32 on a complex or Gaussian plane. We can now call the projection of our vector onto the real axis A, and our projection onto the imaginary axis B. Using standard trigonometry, we can label this angle theta and make a series of conclusions from our triangle. The vector has a magnitude length of r is equal to the square root of a squared plus b squared. A is equal to r cosine of theta, thus b is equal to r sine of theta. We also know that theta is equal to the inverse tangent of b over a. Taking a closer look at our triangle, we can use a and b to construct our complex number z in this form. Remembering the trigonometric values that we gave our lines a and b, we can substitute these values into our complex number and simplify. If you remember Euler's formula from the beginning, you can probably see that we can just replace our sine and cosine with e to the j theta. We then condense our complex number into this expression. It can also be written in this shorthand form. So now that we've come up with ways to define and manipulate complex numbers, let's take a look at each form. We first have our rectangular form. We also have a trigonometric form using sine and cosine. We then used Euler's formula to solve for this expression in our complex exponential form. The final form is our polar shorthand form using the angle symbol. All of these various forms are ways to express complex numbers, and each have their respective use depending on the context and situation. All of this classification for complex numbers is great and all, but why do we care as electrical engineers? You may have seen this symbol on a circuit schematic. This is a AC voltage source. A generic AC voltage source can be expressed by a V0 amplitude with a frequency omega. We can convert this into a polar trigonometric expression by adding our imaginary term. We can add this term because it has no physical meaning and doesn't affect the real voltage, but we will need it for the math ahead. Condensing the expression for our AC voltage source further, we can create another graph to show the real-life application of our first graph. We then have our angle, omega theta, the max value of V, which is V0, and its respective projections on the real and imaginary axes. So how does representing a sinusoidal voltage source as a complex exponential actually help us? Well, given the voltage of our generic case for an alternating source, we can use this voltage to find a complex expression for our current. Using Ohm's law, we just divide our complex exponential by the resistance. So, given our most used passive circuit components as shown above, we can solve for the current through a resistor. We can also solve for the current through a capacitor, as well as an inductor. I've completed the algebra and calculus in the expressions below for these values of current. Looking at our calculated expressions for current below, we can come to valuable conclusions about how current works in each of these components. There is no J coefficient in our current expression through a resistor. Therefore, we can conclude that the current is in phase with the voltage that I have in blue. Given the J term found in the capacitor equation, we can now conclude that current leads voltage in a capacitor. This is due to a capacitor's tendency to resist sudden change in voltage. We see that the exact opposite happens in an inductor. An inductor resists change in current. Therefore, the voltage must rise or fall first in order to create the desired change in current. So now that we've gone over complex expressions for voltage and current, we can now learn about impedance. We use Ohm's law once again to derive the complex form of resistance for each circuit component. Taking our complex expressions for voltage as well as current, we can come up with a value called impedance, often written as a Z. The X in our other expressions stands for capacitive reactance and inductive reactance, but they can be treated as impedances when solving an AC circuit. The expression above is AC Ohm's law, where our equation is frequency dependent. This makes sense given that inductors and capacitors are essentially frequency-sensitive resistors. Thus, we can treat our impedances as we would treat resistors in a DC circuit. Using impedances for AC circuit analysis can take away the headache of differential equations. In this example, we have an RLC series circuit with an AC voltage source. Because these components are in series, we can label each of these components Z1, Z2, and Z3. Their respective values are now shown on screen. We can calculate the total impedance by adding Z1, Z2, and Z3 together. If we want to solve for current, all we have to do is plug our expressions into this equation in order to find our alternating current. Although the algebra may be tough, this method can be easier than solving systems of differential equations. Before the end of this video, I want to make another quick point about impedance. On our now familiar complex plane, we can see clearly that Z sub r is located only on the real axis and therefore has an angle of 0 degrees. Taking a look at our capacitive reactance, the J in the denominator gives us a vector pointing downward. This means it has an angle of negative 90 degrees. Our inductor is not surprisingly the exact opposite. It features a j omega term in the numerator, and its angle happens to be 90 degrees as shown. These expressions can tell us about how these components function given different frequencies. For an inductor, a large omega would act like an open circuit, while a very small omega would act like a short circuit. A resistor is not dependent on omega, therefore there is no change. For a capacitor, however, the omega in the denominator means a large omega acts like a short circuit, while a DC source or small omega would act like an open circuit. This frequency response information is unbelievably valuable. So whether we are working with super high frequencies as shown here, or maybe we're working with lower frequencies, we can use these components to control amplification and attenuation of certain frequencies. Now for a quick recap. We now see the value of using complex numbers to come up with general expressions for voltage, current, and resistance. These complex expressions give us intuition for how these principles operate. Complex impedances are of particular use in breaking down AC circuits, and they also give us more information about frequency response and possible filtering techniques. If you enjoyed this video, make sure to like and subscribe for more content just like this.
Half of your day is gone, and sure, you worked, but were you productive? Introducing Coda AI, your new work assistant.